Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. So, we are continuing in module 9. So, where we have already discussed about two applications. So, today we are going to study about the third applications, that is on a manufacturing process. So, we will take the turning operation as the application and we will study. So, if the vibration of the tool or the vibration of the workpiece to be nonlinear, and we will derive this equation of motion and see how to solve this equation motion. So, in the previous 2 weeks, so you have studied regarding this energy harvester and also vibration observer. So, where we have studied regarding the passive and active vibration observer. So, in case of energy harvester, so we have seen how this piezoelectric excited cantilever beam can be used as a energy harvester. So, in that case, so we have taken both external and internal resonance conditions and we have studied the governing equation of motion, and then we have solved those governing equation of motion and we have seen how we can obtain this voltage from this vibration, or we can harvest the energy from this ambient condition. So, in case of vibration observer, so which can find many applications in industry. So, we have seen the passive type of vibration observer and active type of vibration observer. So, today we will extend our analysis to a manufacturing process. So, where we are going to study regarding the vibration of the tool and workpiece in case of the turning operation. So, the first work I will show you. So, this is part of the PhD work of my PhD student Dr. Arnab Chand, and some of this work have been already published in the Journal of Sound and Vibration. And so, this work, so you just see regarding this nonlinear dynamic analysis of parametrically excited tool in turning operation with delay and internal resonance. So, here we are going to consider the delay and also the internal resonance condition, and we will find the instability regions to study the conditions in which there will be no vibration. So, this is the turning operation. So, you can see the turning operation. So, in this turning operation, so we have a workpiece and this is the tool. So, the tool holder can be modeled or tool is supported, the supporting condition of the tool can be modeled by using the spring and damper system. So, it can be modeled. So, here we are assuming the workpiece to be rigid and the tool to be flexible. So, as we are considering a flexible tool, so here this flexibility is represented by using the spring constant or spring and damper in both x and y direction. So, in x direction, so we have taken this vertical direction. So, this is x direction and the horizontal direction as y direction in this case. So, here, so the spring in x direction is taken to be kx and the damper is taken to be cx, and in y direction it is ky and cy. As the workpiece is rotating, so we assume the workpiece is rotating with omega, capital omega. So, there is initial undulation in the cutting. So, you can see, so initially, so due to this undulation, so this is the chip. So, you can see this is the chip, and so the chip thickness is represented by h. So, we will see that thing. So, here initially it is h0 and after some time, so it will be hc. So, we have to find how much force is acting on the by the tool on the workpiece, or the how much force is exerted by the workpiece on the tool in a reverse direction. So, this is the feed direction. So, the equation of motion of the tool can be written in both x and y direction. So, in the cutting force direction and feed direction. So, this is the feed direction, y is the feed direction, and this is the cutting force direction. So, x is the cutting force direction and y is the feed direction. So, in cutting force direction, the equation of motion can be written equal to mx double dot. So, in x, so this is the cutting force direction, x is the cutting force direction. So, if the displacement is x in cutting force direction, so it can be written as mx double dot plus cx x dot plus k x1. So, we have written this is k x1 t, k x1 into x t plus k. So, we are taking a cubic. So, we are modeling the spring as a nonlinear spring. So, generally in most of the literature you can find they have taken this linear spring. So, here it is taken to be a nonlinear spring. So, that is why this k x is represented by k x1, this is the linear part, k x1 x t, and the nonlinear part is written k x3 x q. So, we are taking a cubic nonlinear spring. So, this way we can model the spring force as k x1 t into x t plus k x3 into x cube. So, this will be equal to the cutting force, that is x f x. So, cutting force f x, this cutting force can be written by using this equation, that is k x w into h cube. So, similarly in case of y direction, so this is the y direction, this horizontal direction is the y direction. So, in this, or the feed direction. So, in the feed direction, so the equation motion can be written as m y double dot plus c y y dot plus, similarly here in y direction also we have taken this cubic nonlinearity. So, that is why it can be written k y y t plus k y 3 y cube. So, this will be equal to minus f y. So, this is the feed direction. So, the workpiece will exert a force on the tool. So, that is why it is written as minus f y, that is equal to minus k y w into h to the power q. So, where h, so that is the chip thickness, can be written as, so this is equal to V t plus y t minus y t minus tau. So, here you just see this is t minus tau. So, this is the tau is the time delay. So, delay term is used here. So, before previous cut, let the previous cut in y direction, what is the displacement, and this present cut, what is the displacement, and into, so this is the V t. But because of the vibration in the cutting force direction, so omega r tau will be equal to 2 pi r plus x t minus tau. So, substituting these two in this equation and writing that h equal to v tau x t plus y t minus y t minus tau x t. So, we can write this equation in this form, that is x double dot plus e by m x dot plus k x 1 by m x plus k y 3 by m into x cube. So, this is k x 3. So, this is not y. So, this is k x 3 by m x q. So, this will be equal to k x w by m into v tau x t plus y t minus y t into y t minus x tau to the power q. So, similarly, in the y direction equation can be written as y double dot t plus c y by m y dot t k y 1 by m y t k y 3 by m y cube equal to minus k y w by m into, similarly we can put this equation w and h q in this form. So, h replacing h in this way. So, it will be equal to v tau x t plus y t minus y t minus tau x tau to the power q. So, here the tool is assumed to be rigid and the tool is assumed to be flexible and the workpiece is assumed to be rigid. So, that is why we got these equations. So, here we have taken the delay also into account to find what is the chip thickness, actually due to undulation. So, it will depend on the previous cut. So, the chip thickness will depend on the previous cut. So, that is why, so taking that into account, so it can be written in this form. So, now assuming this x to be equal to x 0 plus zeta and y equal to y 0 plus eta. So, at time t, for example, x equal to x 0 and time t y equal to y 0. So, at any time t, so this x can be written as x 0 plus zeta and y equal to y 0 plus eta. So, that is why this equation can be now further written in this form, that is x double dot can be written as x 0 double dot plus zeta double dot and x 0 double dot plus zeta double dot plus c by m c x by m x 0 dot plus c x by m zeta dot k x 1 by m x 0 plus k x 1 by m zeta plus k x 3 by m into x plus zeta cube equal to k x w by m. So, v tau into x 0 plus zeta plus y 0 plus eta minus y 0 t minus tau 0 minus eta into t minus tau 0 to the power cube. So, this q actually the a number. So, depending on the conditions of the cutting operations. So, from experimentally this number is can be determined. So, for different materials and cutting conditions, so q will be different. So, in the numerical analysis we will see what is the value of q is taken in this case. So, if we will substitute x equal to x 0 in this equation, we will obtain. So, this if x 0 is the steady state condition. So, if we substitute x equal to x 0, then this equation becomes, so this x 0 double dot plus c by m x 0 dot plus k by m x 0 plus k x 3 by m x 0 cube equal to k x w by m into, so this parameter to the power q. So, as in case of the static deflection, taking x 0 as the static deflection. So, this part will be equal to 0. So, then so now neglecting this part, so the remaining part can be written as zeta double dot. So, due to steady state condition, so one can take this is equal to k by m x 0 t plus alpha 1 3 by m x 0 cube equal to k x w by m v tau to the power q. So, this is the condition one can take. So, now so the equation will reduce to this form, that is zeta double dot plus c by m zeta dot plus k x by m zeta plus 3. So, you just see when you expand this term, that is x plus zeta cube. So, here you have put x equal to x 0 plus zeta cube. So, you just see, so if you expand this thing, then this becomes x 0 cube plus zeta cube plus 3 x 0 square zeta plus 3 x 0 into zeta square. As zeta is very small, the zeta cube and higher order terms can be neglected, or if you want to keep also, you can keep this up to cubic nonlinear term, and so there will be a term of 3 x 0 square into zeta and another term with 3 x 0 into zeta square. So, the perturbation will contain all these terms. So, that is why, so this additional term you can see. So, zeta double dot plus c by m zeta dot k by m zeta. So, this is the additional term you are getting, that is 3 k x 3 by m x 0 square zeta plus k 1 by m zeta plus 3 k x 3 by m into x 0 into zeta square and plus k x 3 by m zeta cube plus k x w by m v tau to the power q. So, it will be equal to k x w by m. So, v tau x 0 t plus eta into eta t minus tau 0 to the power q. So, this is due to the time delay term. So, now this can be written as k x w by m. So, v tau x 0 t to the power q plus k x w q by m. So, this is equal to or in v tau x 0 t to the power q minus 1 into this is the term it can be written. So, now we can keep or rewrite this equation in this form, that is zeta double dot plus c by m zeta dot plus. So, we can combine the term with zeta. So, this becomes k x by m plus 3 k x 3 by m into x 0 square zeta. So, you just see. So, now the coefficient of zeta, so equal to k x by m plus 3 k x 3 by m x 0 square. So, it depend on the initial condition, that is initial x 0. So, this will be the coefficient. So, this coefficient is generally the nonlinear natural frequency of the system. So, that is omega n square. So, plus 3 k 3 by m x 0 zeta square plus k x 3 by m zeta cube. So, we have a quadratic term and a cubic term, and other parts we have taken to right hand side. So, which can be acting as a forcing term. So, here we can take this rho equal to v by omega r. So, this omega r into rho equal to v we have taken. So, that is why this rho equal to v by omega r. So, it is written in terms of, now it is written in terms of rho. So, right hand side is written in terms of rho. So, these are the parameters one can use. So, for example, one can to write this complicated equation in a simplified form. So, one can use these parameters, for example, alpha 1 one can use equal to k x 1 by m plus 3 k x 3 by m x 0 square. So, it will represent the natural frequency of the system, square of the natural frequency of the system. Similarly, alpha 2 1 can be taken k y 1 by m plus 3 k y 3 by m into y 0 square. So, this non-dimensional time can be written as this t bar equal to root over alpha 1 1. So, that is omega t. So, for example, generally we take this t bar equal to this is non-dimensional time equal to omega into t. So, this for the x direction we have taken this is equal to omega 1 1 or alpha 1 1. So, this is radian per second into radian per second into second. So, this becomes radian. So, that is the angle. So, we are taking this non-dimensional time t bar. So, t bar equal to root over alpha 1 1 t, then tau bar. So, this is the delay time also we can non-dimensionalize that thing. So, delay time also can be written root over alpha 1 1 into tau omega 1 1 square equal to. So, this is the non-dimensional omega 1 1 we are taking. So, omega 1 1 square equal to alpha 1 1 by alpha 1 1. So, you just see we have taken it in such way that this term becomes 1. So, then omega 2 1 this is alpha 2 1 by alpha 1 1. So, mu 1 So, this is to represent the damping, we are taking this mu term. So, mu 1 bar equal to Cx by 2 epsilon. So, here we are keeping or using the bookkeeping parameter epsilon, that is why we have this epsilon here. So, mu 1 bar equal to Cx by 2 epsilon root over alpha 1 bar by m. Similarly, mu 2 bar equal to Cy divided by 2 epsilon root over alpha 2 1 m. Similarly, alpha 1 2 can be written, alpha 1 3 and alpha 2 2, alpha 2 3. Omega bar, this is the frequency, non-dimensional frequency of rotation. So, rotational frequency we have taken equal to capital omega. So, we can non-dimensionalize this frequency, that is omega bar equal to omega by root over alpha 1 bar. So, then this length parameters x by L we have taken z x bar and y by L also we have taken z y bar. So, now removing the bar from this. So, now using this thing, the equations can be written in using a bar form. So, that removing this bar we can have these two equations. So, one in zeta direction, one in zeta and other in eta. Zeta is in x direction and eta in y direction. So, our equation now reduced to zeta double dot plus 2 epsilon mu 1 omega 1 1 zeta dot plus omega 1 1 square zeta plus epsilon square alpha 1 2 x square plus epsilon square alpha 1 3 x cube equal to k 1 by k r rho to the power q minus 1 into eta t minus tau plus k 1 by k r rho to the power cube zeta t minus tau 0. Similarly, eta equation in y direction, our equation is reduced to eta double dot plus 2 epsilon mu 2 omega 2 1 eta dot plus omega 2 1 square eta plus epsilon square alpha 2 2 y square plus epsilon square alpha 2 3 y cube equal to minus k 1 rho to the power q 1 into eta t minus tau 0 minus k 1 rho to the power q zeta t minus tau 0. So, here, so this rho is a rotational, is a function of the rotational speed. So, that thing can be written as a constant speed plus a variable speed. So, if we are assuming the variation to be sinusoidal, then we can write this rho equal to rho 0 plus r sin omega t. So, here either, so if it is rotating with a constant speed, then rho will be equal to rho 0, but when we are assuming the rotation to be varying, then that variation we can write in a sinusoidal form. So, that is why it will reduce to, so rho can be written as rho 0 into 1 plus r sin omega t. So, here you just see, so we can write now this equation in this form. So, it can be written x double dot. So, now replacing, we can write down this equation in this form, that is x double dot plus 2 epsilon mu 1 omega 1 1 x dot plus x plus, so this zeta is replaced by x and this eta is replaced by y for better understanding. So, now it is written in this form, that is x double dot plus 2 epsilon. So, these two equation you can check. So, here we got this omega 1 1 equal to, as we are writing in this form. So, x double dot plus 2 epsilon mu 1 omega 1 1 x dot plus x plus epsilon square alpha 1 2 x square plus epsilon square alpha 1 3 x cube equal to epsilon k 1 1 1 plus epsilon q 1 1 sin omega t into y t minus tau plus epsilon square k 1 2 1 plus epsilon q 2 2 sin omega t x t minus tau 0. Similarly, in this y direction, this is the equation can be written. So, here we have taken this q 1 1 equal to r q minus 1 by epsilon, q2 to r q by epsilon, k1 equal to ky w q 2 pi r to the power q minus 1 divided by k1, and that is equal to ky w q 2 pi r to the power q minus 1 divided by m1 omega 1 square. Similarly, kr is taken to be ky by kx, k11 equal to k1 rho 0 to the power q minus 1 by kr epsilon, k12 equal to k1 rho 0 to the power q by kr epsilon square, k21 equal to k11 into kr, k22 equal to k12 into kr, and mu equal to mu1 equal to. So, here taken mu equal to mu1 equal to mu2. So, considering symmetric, so we can write down these two equation in this form. So, now, so as we got the governing equation of motion, so you just see this equation is not similar to that what we have studied in case of the Duffing equation, particularly in the right hand side the equation, the forcing part in the Duffing equation is not similar to the part we have written it here. Here the forcing is slightly different, it is written in a slightly different way, but so the left hand side contains these quadratic and cubic nonlinearity. So, if it is equal to 0, so we can have a Duffing equation with both quadratic and cubic nonlinearity. Actually, you know, in a governing equation, so we can have two parts, the complementary part and the particular integral. So, the complementary part also will contribute to the vibration of the system, that is the free vibration of the system, and these particular integral will be due to the forcing part of the system. So, now we have to solve these equations. You just see this equation is written in the form of a delay differential equation. So, here the delay part is considered in this equation. So, this is the delay differential equation. So, you can solve this delay differential equation using this DD20. So, using DD23 command of the MATLAB, or you can write your own equation solver to solve these things. Also, we have discussed previously that by using this Runge-Kutta method also you will be able to find the solution of this nonlinear governing equation of motion. So, let us take the example or how to solve it using this method of multiple scale. So, as you have seen, due to the presence of the nonlinearity, so it will not yield any closed form solution. So, as it is not, or we are not having any closed form solution, so we can go for some approximate solution. Approximate solution can be obtained by using many different methods, such as method of averaging, method of Lindstedt-Poincare method, or homotopy method, and normal form methods, method of multiple scales also. So, here method of multiple scales is used to solve this equation. So, here for the x and y we can take the conventional expansion. So, here up to second order expansion is taken. So, x is taken to be x11 t0 t1 plus epsilon x12 t0 t1 plus epsilon square x13 t0 t1. Similarly, y is taken to be y11 t0 t1. So, this is t0 t1 plus epsilon y12 t0 t1. So, that for t1. So, this is t0 t1 can be written. So, here tn. So, you can recall that tn is nothing but epsilon to the power n t. So, tn. So, that is why t0 equal to t and t1 equal to epsilon t and t2 equal to epsilon square t. So, these are the different time scales similar to the time scale we are using in our watch, that is for example, this hour hand, this minute hand and the second hand. So, here we are taking 3 different time scale, that is T0 equal to T, T1 equal to epsilon T and T2 equal to epsilon square T, where epsilon is a bookkeeping parameter which is very less than 1. So, as it is very less than 1, so this T1 and T2 are further less and less than this time scale T. So, now for the delay part, you can note for the delay part we can use in a similar way. So, xd is written as x11d T0 minus tau. So, this T is replaced by T minus tau. So, T is replaced by T minus tau for the delay differential equation or delay part. So, delay time can be written by using T minus tau. So, this T0 can be written as T0 minus tau. Similarly, T1 can be written multiplying epsilon, we can write this is T0 minus tau. So, this epsilon T0 is nothing but, so this is equal to epsilon T0 minus epsilon tau. So, this epsilon T0 is nothing but our T1 time scale. So, this is T1 minus epsilon tau. So, that is why it is written T0 minus tau, T1 minus epsilon tau. Similarly, we can have this epsilon square for T2, it will be epsilon square T0 minus tau. So, it will be epsilon square T0 is nothing but T2. So, it will be T2 minus epsilon square tau. So, that way it can be written. So, this xd, that is the delay. So, this is the displacement in the previous chord, that is xd can be written equal to x11d T0 minus tau, T1 minus epsilon tau and T2 minus epsilon square tau. So, this is plus epsilon x1d 12d T0 minus tau, T1 minus epsilon tau, T2 minus epsilon square tau. Similarly, so we can go up to epsilon square. So, epsilon square x13d into T0 minus tau, T1 minus epsilon tau, then it will be T2 minus epsilon square tau. Similarly, yd can be written using this y11d, y12d and y13d. So, writing this x, y and the delay part of it in this form and using this d by dt equal to d0 by d0 plus epsilon d1 and d square by dt square equal to d0 square plus 2 epsilon d0 d1. So, we can reduce our equation and then separating of the order of epsilon. So, we can different order of epsilon, that is epsilon to the power 0, epsilon to the power 1, epsilon to the power 2. So, we have these equations. So, our equation reduces to d0 square x11 plus omega 11 square x11 equal to 0, d0 square y11 plus omega 21 square y11 equal to 0. So, actually while writing this equation you must take care so that the right hand side forcing term will be of the order of epsilon. So, that in the first case, that is epsilon to the power 0, the right hand side you will get 0. So, this will happen. So, in case the system is weakly, the forcing is weakly nonlinear. So, if the forcing is strong, then in that case in the right hand side you will have a forcing term. So, which not will be equal to 0 and your equation of motion, the solution of this equation will be different. It will be similar to that what we have studied in case of the hard excitation. So, now this equation is similar to what we have studied in case of the weak excitation. So, that is why in the right hand side we have 0 0 term. So, our equation is reduced to this d0 square x11 plus omega 11 square x11 equal to 0, d0 square y11 plus omega 21 square y11 equal to 0. So, already we know the solution of this thing where x11 can be written by using. So, this is a second order differential equation. So, by taking two constants it can be written. Similarly, now for the after we get the solution for x11 y11, so we can substitute it in the second equation, and then getting the solution for this x12 and y12, we can substitute those things in the third equation, that is of epsilon square, to get the required expression. So, here you can recall that we have to find the secular terms, and eliminating those secular terms will get the reduced equation. So, you just see, as we are taking up to epsilon square, so you can take up to epsilon cube. So, this equation is written up to epsilon cube. Now, the solution of this one, solution of d0 square x11 plus omega 1 square x1 equal to 0, and this d0 square y11 plus omega 2 1 square y11 equal to 0. So, in this form, so it is equal to a1. So, as this a1 and a1 bar will be constant, so they will not be function of t0. So, that is why they may be function of t1 and t2, that is why it is written a1 t1 t2, it is not written t0. So, you can note that it is not a function of t0. So, x11 t0 t1 t2 can be written as a1 t1 t2 sin e to the power I omega 11 t0 plus a1 bar t1 t2 e to the power minus I omega 11 t0. So, here, so you can note that, so these a1 bar is the complex conjugate of a1, a1 bar, a1 and a1 bar are complex number, and this a1 bar is the complex conjugate of a1. Similarly, so we can write down the second equation y11 equal to a2 t1 t2 e to the power I omega 21 t0 plus a2 bar t1 t2 e to the power minus I omega 21 t0. Similarly, y11d can be written a2d. So, a2 will be replaced by a2d, t1 t2 can be written e to the power I omega 21 t0. So, t0 will be replaced by t0 minus tau. Similarly, a2 bar d equal to a2 bar d t1 e to the power minus I omega 21 t0 minus tau. Similarly, this x11 d can be written equal to a1. So, it will be a1d. So, here we are using this a1d t1 t2 e to the power I omega 11. So, this t0 will be replaced by t0 minus tau plus similarly a1 bar d e to the power minus I omega 11 t0 minus, so it will be t0 minus tau. So, this way it can be written. So, now writing this x11, x1d, y11, y1d. So, we can substitute this equation in this equation. So, you just see, only we will take these two terms in the left hand side. So, this equation can be written d0 square. So, if you recall, so d0 square x12 plus omega 11 square x12 omega 11 square x12. So, other part will shift it to the right hand side. Similarly, the second equation also will write this is equal to d0 square y12 plus omega 21 square y12. So, other part will shift to the right hand side. So, you can note that this other part is a function of both. So, it is a function of both x11, x11, y11 and x1d, 11d and y11d. So, these are function of both x and the delay part of the system. So, that way we can write down these equations. So, now substituting the solution there, so we can get. So, now we can eliminate the secular terms. So, by eliminating secular terms, so our equation will reduce to this form, and so as you know that as the equation do not have any particular solution, the non-transient solution of these equations will be x12 equal to x12d equal to y12 equal to y12d equal to 0. So, by putting these for steady state, actually x12 x12d equal to y12 and y2d equal to 0. So, we can have this equation. So, now we have this equation. So, substituting the solution of the x13 x13d y13 and y13d in the secular term. So, we can obtain a set of equations like this, and here also now what we can write. So, we can write this taking these a equal to half a e to the power I theta form. So, we can write a equal to, as a is a complex number. So, we can write a equal to half a e to the power I theta, and this d a I by dt, that is d a 1 by dt for example, will be equal to d by dt half a 1 e to the power I theta 1. So, which will be equal to epsilon d 1 a 1 plus epsilon square d 2 a 1 plus epsilon cube d 2 a 1. So, in that way if we can write, so we can have these 4 equations. So, these 4 equations, that is a 1 dash, a 1 gamma 1 dash, a 2 dash and a 2 theta 2 dash. So, this can be written in terms of gamma 2 dash, because we are reducing this theta to gamma form to make the equation in non-autonomous form. So, theta 1 can be written theta 1 minus theta 1 plus theta 2 plus T 1 sigma 2. So, here we are using the de-tuning parameter sigma 1 and sigma 2. So, minus theta 1 plus theta 2 plus T 1 sigma 2 equal to gamma 2, and minus 2 theta 1 plus T 1 sigma 1 equal to 2 gamma 1, and it can be written this minus theta 1 minus theta 2 plus T 1 sigma 1 minus T 1 sigma 2 equal to minus gamma 2 plus 2 gamma 1 and minus 2 theta 1 plus T 1 sigma 1 minus 2 T 1 sigma 2 equal to 2 gamma 1 minus gamma 2. So, by writing in this form, so our equation is reduced, and it can be observed that due to the presence of the term a 1 gamma 1 dash, the trivial state conditions will not contain the perturbation. So, it can be, so we cannot obtain the stability from the earlier equation. So, now we have to make the transformation in such way that, so we will get distinct equations which can be perturbed to get the stability equation. So, here we can assume this P 1 equal to a 1 cos gamma 1, Q 1 equal to a 1 sin gamma 1, P 2 equal to a 2 cos gamma 1 minus gamma 2, and Q 2 equal to a 2 cos gamma 1 minus gamma 2, Q 2 equal to sin a. So, it will be a sin, so it will be a sin gamma 1 minus gamma 2. So, then substituting these equations, so we can obtain this P 1 dash, Q 1 dash, P 2 dash and Q 2 dash equations. So, which we will perturb to get this delta P 1 dot delta Q 1 dot delta P 2 dot and delta Q 2 dot. So, this thing can be written equal to this Jacobian matrix into delta P 1, delta Q 1, delta P 2, delta Q 2. So, in this form can be written, and so this is the Jacobian matrix. So, now finding this eigenvalue of the Jacobian matrix, so we can find whether the system is stable or not. So, as we are interested for the trivial state stability region or to find the instability region. So, we can find for the system parameter for which the system becomes stable or unstable. So, if the real part of the Jacobian eigenvalues of the Jacobian matrix is positive, then the system is unstable, and if the real part of the eigenvalues of the eigenvalues are negative, then the system is stable. So, taking these conditions, so we can study the stability of the system. So, here these parameters have been taken. For example, we have taken the tool length to be 150 mm. So, tool cross section 20. So, it is a square cross section we have taken 28 into 28 mm square. So, tool fast natural frequency, it can be observed that it is around 988 Hz. Tool second natural frequency. So, as we are taking a square cross section, so it is same, that is 988. So, tool material is taken steel. So, density is taken to be 7.85 minus 6 kg per mm cube. So, this tool mass we have taken only 0.92 kg, and workpiece radius to be 12 mm. So, chip width, that is 0.3, feed rate is taken to be 0.2, workpiece rotational speed is 3 radian per second. So, force coefficient in cutting force direction Newton per mm square, this is taken to be 1500, and the force coefficient in feed force direction, so it is taken to be 450. So, taking these parameters, so the other parameters are obtained. The coefficient are mainly function of sine and cosine of omega 1 tau and omega 2 1 bar tau, where tau equal to omega 1 bar tau is the angle in radian using the relation tau bar equal to root over omega 1 bar t. So, omega 1 bar and omega 2 1 bar are non-dimensional and has unity value. So, we have taken it is in such way that, so they have the unity value. The values of sine and cosine of omega 1 tau and omega 2 1 tau will be repeated in the range of 0 to 2 pi. So, based on the sine and cosine in case of the steady state condition. So, this value, taking this value, so the tau term have been determined and they have been taken in the analysis. So, here you just see the other parameter what we have taken in this analysis, m1 equal to 0.92. So, here it is written the mass is taken to be 0.92. So, that is why m1 is taken to be 0.92, kx1 equal to 3.6 into 10 to the power 4 Newton per mm, ky1 3.6 into 10 to the power 4 Newton per mm, kx3 equal to 30 Newton per mm3, ky3 30 Newton per mm3. As we are taking this cross section, square cross section, so the stiffness are taken similar in both x and y direction. So, kc is taken to be 1500 Newton per mm square, kf equal to 450 Newton per mm square, r equal to 12 mm, wc equal to 0.3 mm, and V0. So, you just see this is the feed taken to be. So, feed V0 equal to 0.2, V0 equal to 0.2 millimeter per second. So, Q, that coefficient that power term you have seen Q. So, Q is taken to be 0.75, and this is taken, this rotational speed of the spindle is taken to be 3 radian per second, and R is taken to be, so this is the scaling parameter R, so that is taken to be 0.1. So, taking all these parameters, so you can observe that the coefficients are coming to be in the, so coefficients are coming in the proper order. So, using scaling factor R1 equal to 0.001 and bookkeeping parameter epsilon equal to 0.01, the following non-dimensional system parameters are obtained. So, that alpha 13 equal to 8.33, alpha 23 8.23, Q12 minus 2, Q22 equal to 8 and K1 equal to 0.005, K11 equal to 6.55, K12 equal to 3.64, K21 1.96, K22 1.09, omega 11 you just note. So, it is non-dimensionalized in such a way that this omega 11 equal to 1 and omega 12 also equal to 1 and mu 1 equal to 1 and mu 2 also it is coming to be 1. So, taking these parameters, so and from the Jacobian matrix, so one can find the stability just by finding the eigenvalues and checking the eigenvalues. So, for different value of V1 and sigma, so that is the feed rate, so and sigma 1 is the detuning parameter. So, you can get this in stability region. So, the region outside this curve is stable, inside this is unstable and outside it is stable. So, the operator has to take the feed rate and also the rotational speed in such a way that it should in the stable region to have a vibration free or there will be no vibration of the tool. So, if it is within this range in this instability region, then the tool will vibrate. So, the obtained region so will be very much useful to find the operating conditions for which there will be no chatter in the turning operation. So, here the instability region under internal resonance condition, here we have taken. So, you just see we have taken this omega 21 equal to omega 11. So, that is why, so we have this as this is 1:1. So, we are considering this 1:1 internal resonance condition in this case. And along with these things, so we are considering the principal parametric resonance conditions also, that is capital omega equal to 2 omega 11 plus epsilon sigma 1 and omega 21 equal to omega 11 plus epsilon sigma. So, this is scattering the internal resonance condition and this is scattering the condition for, though we can tell this is external resonance condition, that is principal parametric resonance condition, but this is due to the rotational speed, the variation in the rotational speed in a periodic way. So, due to that assumptions we are getting this thing. So, sigma 1 is non-dimensional detuning parameter for principal parametric resonance and sigma is non-dimensional detuning parameter for internal resonance condition. So, you can observe that. So, instability zone for tool in sigma V1 plane for the different value of delay. So, 3 different values of delay has been taken. So, in the first case the delay is taken to be 5 pi by 4, in the second case it is 6 pi by 4 and in this third case it is 7 pi by 4 for mu equal to 0.69, 0.97 and 0.69 respectively, considering q equal to 0.75 and V0 equal to 0.2 millimeter per second. So, you can observe how the instability region varies. So, in this case, in the last case, the instability region when the delay is taken to be 7 pi by 4. So, it is to be, so you can have a very small instability region and for the most of the cases the system remain in stable region. So, taking different delay conditions, so one can actually obtain this instability region and the operator will get the sense to operate it at a system parameter where the system will not have any vibration or there will be no chatter in the system. So, the instability region and under this internal resonance condition for principal parametric resonance it is studied here. So, here tau is taken to be 3 pi by 2, q equal to 0.75 for different feed rates. So, 3 different feed rates have been taken. So, first curve is for feed rate V0 equal to 0.18, second mu or first case V0 equal to 0.18, mu equal to 0.01, for the second curve, so you can see with V0 equal to 0.2 millimeter per second, mu equal to 0.0097, and for the third curve you can see V0 equal to 0.25 millimeter per second and mu equal to 0.007. So, here also you can see, so in this third case we have more stable zone and the operator can operate it freely in this or for a wide range of system parameter. Similarly, so we can vary different parameters and study the instability region. So, in addition to the parametric instability region, so one can plot the frequency response plot also. So, in this unstable range, so if someone operate this thing in unstable range, for example, one want to have the texture in the turning operation. So, in that case, so he can operate it in the unstable region. So, when it is operated in this unstable region, so it is one should know the frequency response plot and one can find, so how much response or how much vibration will be there in the system or in the tool. So, if one can plot the frequency response plot, so one can see that this point correspond to the supercritical pitchfork bifurcation point and this correspond to the subcritical pitchfork bifurcation point. So, here, so in the supercritical pitchfork bifurcation point, so after the supercritical pitchfork bifurcation point with increase in the sigma, so that is with increase in the speed of the rotational speed, so it will vibrate and this response can be obtained. So, from this A1 one can see, so what will be the response. Similarly, for A2, A1, so for a different value of tau it has been plotted. So, in the first case tau equal to 5 pi by 4, second case it is 6 pi by 4 and third case it is 7 pi by 4. Similarly, for frequency response can be plotted for a different feed rate. So, this is the first case, it is plotted for a different tau value, that is delay, and in the second case different feed rate for tau equal to 5 pi by 4, 6 pi by 4 and tau equal to 7 pi by 4. So, this is in the cutting force direction and the second set of figures are in the feed force direction, that is A2. So, this is A1 versus the sigma 1, this is A2 versus sigma 2. So, you can see, so in the first case it is 8 into 10 to the power minus 3, 8 into, and in the second case in y direction, that is in the feed direction, so it is 1 into 10 to the power minus 3. So, in feed direction, so it is less, and in the cutting force direction the response is found to be more. So, this way one can study different frequency and force response plot for different system parameters. So, here the time response is also plotted to show the response in the cutting force direction and in the feed direction. So, 2 points have been taken. So, in this unstable zone, so while taking in this unstable zone 2 points, so you can see there is a vibration, or so due to this vibration there will be chatter mark on the workpiece. So, for different points similarly it has been obtained. So, you can see this undulation is more in this case. So, time response for sigma 1 equal to 0.606 and tau equal to 7 pi by 4. So, one can study different marking, or one can study different response of the turning operation in this way. So, in today class, so we have discussed regarding the vibration of the tool. So, one can similarly study the vibration of the workpiece also. So, here So, this part is given as an assignment to you to study the equation of motion of both workpiece and tool when they are flexible. So, in that case this equation can be written in this form and following in the previous way. So, you can write down this governing equation. So, after writing the governing equation of motion, so you can reduce it to this delay differential equations, and then by solving using method of multiple scale, so you can find the response of the system. So, this part I am not going to discuss in detail, but you can see that using this method of multiple scale and this DDE23, so you can verify that the results are coming to be similar or same. So, the advantage of using this method of multiple scale is that in addition to getting the time response, accurate time response, you can get the frequency and force response plot of the system, and the analysis can be extended to know the effects of different system parameter on the turning operation. So, initially we have plotted this instability region. So, from the instability region we know the zone at which the system will not vibrate or the tool will not vibrate. So, in this case there will be no vibration of the tool and the workpiece. So, knowing those regions, actually we can operate the system in that range so as to get the response of the system. Here more comparisons have been given between DD23 and method of multiple scale, second order method of multiple scale, and these are the instability regions plotted. So, when both the tool and workpiece are flexible, so this is the instability region. So, previous case when only the tool was flexible, so you have seen we had a wide range of stable region, but in this case, so the stability region is reduced because both the tools and the workpiece are vibrating. So, these are the instability region you can plot, and you can see between this instability the response will, in the unstable range the response will grow as the response is growing. So, there will be mark on the tool, or mark will be, there will be mark in the workpiece. So, there will be chatter mark in the workpiece. So, we have to avoid those chatter marks. So, the system has to be operated in the stable range. So, this way you can study different manufacturing system. So, this is the turning operations I have told. Similarly, you can extend this work for the milling operation. Also, you can derive this equation for the forming operation like this rolling operation. So, in many manufacturing system actual the process is nonlinear. So, you can extend your analysis, your linear analysis to the field of nonlinear analysis, and you can find the operating system parameter for which the systems will be stable, and you can operate the system in the stable zone to have chatter free surfaces in the workpiece. So, thank you very much.